today. We just learned, now you have the notes here. I'm going to teach you today how to do the order of the reaction K, in other words, the rate law expression in and of itself, from one graph, okay? From a single graph, from a single trial. Turns out, what we just did, okay, what you were just doing in the homework problem 17 to 28, what you did in the lab yesterday with the potassium iodide and hydrogen peroxide, you collected the hydrogen peroxide, I'm sorry, you collected the oxygen gas at the end, and you varied the concentrations of the H2O2 and the Ki. Remember, you kept this guy constant, you doubled him, the rate doubled, he's first order. Kept the other guy constant, doubled him, the rate doubled, he was first order. If they had doubled and nothing happened, what order would he have been? What do you think? They had doubled the concentration and nothing happened to the rate. What order would he have been? Wow. Wow. Amazing. Seriously. Zero order. It all goes back. It's a funny thing. You realize we've been doing this for about 2 weeks now. We're talking about the initial demonstration I did on this with the mechanism. If someone's not in the slow step, they don't have an effect on the reaction rate. That would be zero order. If they're in the slow step, once they have the effect on the reaction rate, whatever you do to it, it does the same to the rate, same factor. And of course, if he's in there twice, he does it to that same factor raised to the second power. All right, so here's the problem with that system. What do you have to do? You saw how time intensive that is. You have to run multiple trials, varying the dilutions, and then really, because there's so many things that can go wrong when you're collecting these, you really have to do it over and over and over again, like we did. We had like 5 different groups doing it, averaged them all together, and we finally got decent data. Wouldn't it be nice? Is it possible that I could just do one trial, graph the results, and tell if it's first order, zero order, second order? And we can. But it's weird. It involves some knowledge of calculus, which I'm not going to get into because I know everybody hasn't had calculus in here. And the fact is, I hate calculus anyway. But it involves some knowledge of calculus that you really don't need to have. But here's the basis behind it, okay? The basis behind this is more, you don't have to write this down, because actually this is just the theory behind it. And you're going to be writing some things down, but not this. It's often more convenient to determine the rate law expression graphically rather than running multiple trials. It's just very tedious to do that in the lab. So we graph the data 3 different ways, and you'll see the 3 different ways we're going to graph it. The one that shows up as a straight line, whether the straight line's like this or this, the one that shows up as a straight line, that's the guy that tells me, that's the representative graph, tells me the order of the reaction. Now, that doesn't make any sense to you right now, but it will when I show you the examples, okay? Let me show you. First example, if I have a zero order reactant, you have him down there. You want to write this down. If it's a zero order reactant, you guys know this about it, right? He's not involved in the slow step, right? And he apparently has no effect on the reaction rate. Now, you might think to yourself, first of all, how can that happen? How can, for example, an entire reaction be zero order, where the concentration just doesn't matter? You might think that that's not possible. It is possible. It is possible for a reaction to be zero order. Most of the time that happens, it has to do with something that has a solid catalyst, a catalyst. Remember I talked about when we did the platinum nickel catalyst, we're in a lot of our reactions in organic. And, oh, here's a perfect example. You guys should have read by now the pages I told you about with the catalytic converter. Catalytic converter has a surface upon which it attracts the carbon monoxide. And then it breaks it up, activates it, breaks it up, and it combines it into carbon dioxide. All right? So the limiting reactant here isn't the concentration of carbon dioxide. The limiting reactant, believe it or not, is the surface area of that catalyst. That's why. This is a lot to write down here. But basically, you can get a zero-order reaction if a catalyst, especially a solid catalyst, is involved in the reaction where all that matters is its surface area. How much can bind to it. That's the limiting factor, is how many molecules can bind to that surface. Now, if we look at our graphs of these, or after you copy this down, you will see what does not look like a typical graph for a reaction like I was telling you it should look at the beginning of this chapter. And you'll see why. Now, again, that's a lot of theory behind why this would occur. As far as you're concerned, all you got to do is be able to tell which graph of these is the representative graph. So what we would do in a reaction, I don't care what reaction it is, we're going to do this as a lab, by the way, using phenolphthalein and its color change. Okay? We're going to do this as a lab after Christmas. When we get back, we'll do this. We'll run the trials one time, and we'll graph it 3 ways on your graphing calculators. Okay? And here's what you can get. When you get that same data and you graph it 3 ways, oops, sorry, went too far. When you get 3 graphs, here's what you'll get. You already have them there. You don't have to copy them. You get a graph that looks like this, this, and this. Now, a lot of you are looking at that and it's just gibberish to you. Let's see if I can turn some of this into something that makes sense. This is the concentration versus time. Now, when I did a graph of concentration versus time in the past, concentration was here in moles per liter and time over here. First week of school, first week of this chapter, we noticed that the graph looked like this, didn't it? Right? And it looked like that for a very good reason. As the concentrations lessened, the rate lessened, didn't it? Right? And that's why the graph looked like that. We all drew graphs like that. You drew graphs like that in the last worksheet I gave you, too. This graph doesn't look like that. This graph is a straight line. In other words, it doesn't matter what the concentration is. The rate never changes. That's zero order. It doesn't matter what the concentration is. Concentration has no effect on rate. This graph tells me, if I do the graph of concentration versus time and I, for whatever reason, get a straight line, that is a zero order reactant or reaction. Okay? If I get these other 2 crazy graphs at the same time, I'm not looking at them. I'm only looking at the one that's the characteristic graph. All right. Now let's take a look at a first order reactant or a first order reaction. First order reaction, we all know that one reactant controls the overall rate of the reaction. Write that down. We all know that, though, unless it's already written. It's not right there. We already know that. And that is the analogy I use with the, Toy Story widgets, 3 people up here making toys for Santa, okay? Person in the middle, in my case, Kaylin, in this class, was slower than the other one. So she and she alone determine the rate of the reaction. Okay. If I graph that reaction, you know what it looks like? Exactly what I expect it to look like. It looks like this, curve. And I would expect that as the concentration decreases, so does the rate, because there's fewer of them to bang into each other. That's the collision theory. Makes sense. So, if I graph the natural log of the concentration versus time, remember, you're not doing as much lab work in these kind of problems as you are math work, basically graphing calculator work, or computer Excel program work, or whatever. I get a straight line if I graph the natural log of the concentration versus time. Why that happens, I can't go into. Okay, I know some of you who are in a BC calculus might be able to tell me why, right? I bet you some of you can. I noticed you guys had around a packet. Who's the ones who had the packet of being able to tell, like it was a whole bunch of graphs, and you had to be able to pick out what kind of graphs they were. Somebody was walking around with that, I saw it, okay? Now, I'll bet you, Whitner, whoever's teaching that, probably goes over why that graph would look like this, but I'm not going to. All you have to do is worry about this. If you graph the natural log of the concentration versus time, and you get a straight line, that tells me something. That tells me that this is a first order reactant. It is one guy is responsible for this. One guy is in the slow step. The 1 over A does not give me a straight line. And finally, if I do, remember, for each one I have to do all 3 graphs. If I do a second order reaction where I have more than one guy involved in the slow step, guess what? You graph him, 1 over A will give you a straight line. Notice something else about 1 over A. It also gives you a opposite slope. It gives you a positive slope instead of a negative slope. That's going to be important in a minute too, when I kind of summarize all this together. So in effect, you could think of this as a trick. You can think of this as a trick, an easier way to do these. I know they seem to show up all the time. And by the way, this is something I said I've added over the last couple of years. I've just added it because I'm teaching AP. I let this go. I did not cover these graphs. Maybe that would make me a terrible teacher. But the fact is I didn't cover these graphs when covering kinetics in the past because I realized how it was, kind of confusing and kind of memorization if you don't understand the calculus behind it. And it is tough calculus that's behind it. But I've found over the years, as I'm teaching AP, that I have to cover it. It's actually on a lot of the tests. And there is the integrated rate law expression, which you should know how to use as well. I'll talk about how you can get K and the slope, the rate, and basically the entire rate law expression from these graphs, believe it or not. And so let's just basically finish it up with a little summary here, okay? These are your three choices. When you were to go, they're on the back side. You don't have to copy. They're on the back side of your paper. These are your three choices, okay? You have, if you take your data and you graph it these three ways in your graphing calculator, I'm going to show you how to do that. Kind of the same, very similar to the way we did it for the last lab. And you get a straight line here, straight line there, or straight line there. It tells me this is zero order, this is first order, this is second order. Okay? And you're not going to have to, of course, you have to do 3 graphs, but you don't have to do 3 trials or any more than 1 trial in the lab part of it, which is good. All right. Now, let's do a little summary chart. It's also on the back of your paper here. So let's watch this as they come up one at a time. Don't look at your papers for the answers. Just take a look up here as they come up. You ready? If I take a zero order reactant, do we not all agree? If I have a reactant that's zero order, in other words, the people on either side of Kayla, on this side or that side, when they were doing that assembly line, they were not involved in the slow step. Okay, no reactants are in the RDS, by the way, is short for rate determining step. So there's nobody in the slow rate determining step. Okay, the rate law expression, I'm going to explain why this is in the case. Rate will be basically equal to K. All right, that's what it's going to be. That's going to be an entire rate law expression. I'll explain that in a second. The units, I'll explain this in a second, and K is going to be the negative of the slope. And the graph basically is going to be the concentration versus time will be a linear graph. Let me show you about first of all, the rate law expression. We all agree to rate law expression. We learned this already. Rate equals K, A to the X, B to the Y, etc. Okay? If I have a zero order reaction where both guys are zero order, aren't they both 1? So you see why rate basically just equals K? You see? Because these guys are going to cross out of the equation, aren't they? Right? Because they're both raised to the 0 power. Anything to the 0 power is 1. Rate equals K. That's your entire rate law expression. If rate equals K, what are the units of K? Well, what are the units of rate? How do you measure the rate? How do we measure the rate in every example problem in the book? Molar per either minute or second. It's molar per, I put per second here, but it's molar per time. It could be minutes, it could be seconds, it could be whatever, but it's molar per minute because that's what the rate is, that's what K is. They're exactly the same. Now let's take a look at the next one. If I have a first order reactant, there's one reactant in the rate determining step, one in the slow step. Look what the rate law expression now looks like. Rate equals K, A to the first power. Makes sense. First power, that's the that tells me the first order reactant. Look what the units become. Let's see if you can figure out why that is in a second. And in both cases, by the way, why is the slope? Why is K equal to negative the slope? When I rearrange and solve for K, that slope, which direction? Do you remember? Let's go back for a second. Which direction was that slope in those first 2 cases? Right? That's a negative slope, isn't it? So I have to put a negative in front of it, so that's what K will equal. K will equal the negative of the slope, which is already negative, so K is going to be a positive value. All right, so let me show you why this works too. Again, here's your rate law expression for this guy. Rate equals K, A to the first power. Right? Okay, that's it right here. There he is. Why do the units have to be per seconds, which kind of seem like ugly units? Why do the units have to be per second if I have a first order reactant? Well, let's rearrange. K is going to equal rate over A, correct? What do we measure rate in? Molar per second. What do we measure A in? What's the concentration of A in? Molar. Molar cancels. What are you left with? Per seconds. Yeah, you're left with basically 1 over seconds, or a lot of times they like to write it like that. Without me telling you, who can tell me what the units of a second order reaction are going to have to be? Think about it. What I just did there, apply it to a second order reaction. Second order reaction is going to be rate equals K, A to the second power, right? rearrange it in your head. What's K going to be? And then figure out what the units are. What will the units of K be in this case? It'd be, well, K would equal rate, which is in molar per second, over molar squared, correct? One of those m's would cancel out. One of the molars would cancel out. And we'd be left with 1 over molar seconds. Or molar negative first, seconds negative first. Same thing. 1 over molar seconds is that. And that's exactly what you get. Per molar seconds. 1 over molar seconds. Okay? And the rate, of course, there's a rate law expression. 2 guys are in the slow step. What about the slope of that guy? Take a look at that again. Look at this. He's the one guy, when you get a straight line, it's positive. Why? Because you took 1 over the concentration. Why would that change the direction of the slope? Watch. What's happening to the values of these numbers? 4, 8, 12. They're getting bigger, right? Let's take the reciprocal of each of them, which is exactly what you do to get this graph. To get this graph right here. 4, 8, 12, getting bigger. What's happening to the reciprocal of them? They're getting smaller. It's the exact opposite slope. And so in this case, since the slope is now positive, I don't have to take the negative of it like I had to do in this case and in this case. I can just take the positive of the slope. And that's a nice little summary chart, and you're going to be asked to use this all this information in a lab and on the test in questions kind of like this one here. Take a look. I give you this much information. I give you these 3 graphs and this one data table. You are going to collect a data table like this in the lab. You're going to graph it on your graphing calculator 3 different ways. You're going to find that one. And by the way, you notice what the graphing calculator is going to do, or your computer program if you did it on Excel. You're going to say to the computer, make that a linear regression line. Go ahead, tell me what it looks like. And of course, here it is. Does that look like it fits? No. Does it look like this guy fits? A little bit better, but it's not quite there yet, is it? Does that guy fit? Yes. So what kind of a reaction? First question, what's the order of this reactant AB? He must be second order. You see why? He's second order because, and by the way, you're going to get a worksheet like this to do tomorrow also, partly. It's in the air class, they had a double today. So they got it done in about 15 minutes. Okay? You guys will not need more than 15 minutes of the double period to do that tomorrow and hand it in. So it's a second order reaction. Y'all got that? Okay. Can you tell me what the rate law expression would look like for this guy, given that's the equation? Wouldn't you all agree it would have to look like this? Rate would equal K AB squared, right? Because he's second order. And could you find K and the units of this guy? Could you do both? Sure. If you know the slope, and the slope will be that number in front of x, right? Y equals mx plus b. There's the slope. What did it just tell me in the previous problem? The K is. What's the K? K is a positive of that slope. So the K would just be that number. And what would his units have to be? Right, per 1 over molar seconds, correct? Well, not 1 over molar seconds, correct? Now, you see what I'm saying about how this is, it's harder and it's easier. What's easier about this? The easier part about this is really 2 parts are easier. 1, you only run 1 trial. Okay? 2, remember how much time it took me to do those other things? I had to look at, the rate law expression and compare them and see what they were doing. And then I had to plug everybody in to solve for K, right? Do I have to do that now? I don't have to do that. K is the slope. I don't even know, I don't have to worry about the units. The units are always going to be, if it's second order, they're always going to be per molar second. Okay? So it does make that part easier. What's harder about it? Understanding why the heck this is. And I'm not going to ask you about that. I'm not going to ask you to explain why the natural log 1 over the concentration, or well, this one's easy. Everybody can understand that one. But these other 2, why that works, I'm not going to worry about. I'm not going to ask you to explain. That's the only part that's harder. Everything else about this makes it easier when you do it graphically. Okay, so you're going to get a worksheet tomorrow, because I don't want to waste your time. I did the bonus points here yet today. You're going to get a worksheet tomorrow. It's just like this. You'll be able to complete that in 15 minutes. Okay.